Hello everyone and welcome to the online version of the video or the online lecture for section 7.2, which is all about trig integrals. And there's going to be a lot of trig identities and whatnot that come up, but I'll introduce you to them as we come up. One of the key ones, of course, the number one trig identity, sine squared of x plus cosine squared of x equals 1. And we can use this to make seemingly hard-looking integrals a lot simpler. So what do I mean by that? Here's an integral, the integral of sine cubed of x. So there's a few ways we can go about this, but the way we can use trig and trig identities to solve it is we can recognize that this is the same as the integral of sine squared of x times sine of x dx. Right, just sine cubed, that's the same as sine squared times sine. And then, hey, sine squared, that's the same as 1 minus cosine squared. And that just comes from that classic trig identity, sine squared x plus cosine squared x equals 1. So then 1 minus cosine squared gives me sine squared. And now I can use a u substitution. So now I can let u equal cosine of x, and then my du equals negative sine of x dx, and then my integral becomes the integral of 1 minus u squared times minus du, and I guess I can bring the minus out front here, which is the integral of minus 1 plus u squared du. And then this is the type of integral we know how to do. We get minus u plus 1/3 u cubed. And then I got to trade my u's in for my thetas or x's or whatever the variable is. If u is cosine of x, we get this becomes minus cosine of x plus 1/3 cosine cubed of x plus a c plus our constant of integration. Okay, so I used a trig identity to make an integral a lot easier, a trig identity and then a u substitution. So let's see another example of that in action. The integral of sine to the fourth times cosine to the fifth. What can we do here? Well, in general, if one of these powers is odd, we can use the kind of same game plan that we used before. And here, I have an odd exponent. I have a fifth power. So this is the same as the integral of sine to the fourth of x times cosine to the fourth of x times cosine of x dx. And the reason I'm separating out that cosine is the same reason why in the beginning I separated out one sine by itself. It's because that turns out to be really helpful for the u substitution. Because I have an odd exponent here, I can collect an even number of cosines together, and then I have one guy left over, and that'll be useful for a u substitution. And let's see how that looks. So cosine to the fourth, we want to apply our cosine squared plus sine squared equals 1. Let's get cosine to the fourth to look kind of like cosine squared, to make it look like something we know how to work with. So cosine to the fourth, that's the same as cosine squared squared, right? That's just rules of exponents. And now I know what to do with this guy here. Cosine squared, that's the same as 1 minus sine squared. So I get sine to the fourth times 1 minus sine squared x quantity squared times cosine of x. Okay? And then from here, I can let my u be sine of x, and then my du is cosine of x dx. And hey, I've got a cosine x dx right there, so that guy becomes du. And my integral becomes u to the fourth times 1 minus u squared squared du. I replace my cosine of x with du. And now we can expand this whole thing out, and we get the integral of u to the fourth times 1 minus 2u squared plus u to the fourth du. Factor my u to the fourth in, we get the integral of u to the fourth minus 2u to the sixth plus u to the 8th du. And now we can take this integral by applying our standard rules, adding 1 to the exponent and dividing. So we get 2 to the 7th u to the 7th plus 1 over 9 u to the 9th. And then we just trade in our u's for x's. Remember, u is sine of x, so we get 1/5 sine of x to the 5th, which I suppose for some reason we write the exponent here next to the sine. Minus 2/7 u to the 7th, so that's minus 2/7 sine to the 7th of x plus 1 over 9 sine to the 9th of x. And we can't forget our constant of integration, so plus c. Okay, so we know what to do if we have multiple copies of sines and cosines and one of the exponents is odd. We can use this breaking apart. But what do we do if neither exponent is odd? What if both the exponents are even? Well, in that case, we're probably going to want to use one of these formulas here. These are just different trig identities, so I'll run through them right quick, even though you can see them on screen. Sine squared of x equals 1/2 times 1 minus cosine of 2x. So this allows us to write sine squared of x in terms of cosine. Cosine squared of x, it's still written in terms of cosine, but we're dropping the exponent down. Cosine squared of x equals 1/2 times 1 plus cosine of 2x. And then once we have a cosine of 2x, we can apply this formula here. Cosine of 2x is the same as cosine squared minus sine squared. Sine of 2x equals 2 sine x cosine x. Really, the main guys we're going to use are these. These two down here, sine of 2x and cosine of 2x, those are more so just nice to haves. Okay, but what would it look like if we were to actually use one of these in practice? Let's take a look at this. Integral of sine squared of x. Well, it's not an odd number. The exponent here is a 2, not a 3, so we can't do the breaking apart thing. But we just learned that this is the same as the integral of 1/2 times 1 minus cosine of 2x. Right? And so from here, this is a lot simpler to work with because we only have 1's in the exponent. We can get around this by using a u substitution. If we say u equals 2x, then du equals 2 dx. And in fact, that means that dx equals du over 2. So then our integral becomes the integral of 1/2 times 1 minus cosine of u times 1/2 du. Combine our like terms, combine our 1/2s together, we get an integral of 1/4 times 1 minus cosine of u du. And so this becomes, I'll just distribute the 1/4 in, 1/4 minus 1/4 cosine of u du. And again, this is an integral we've seen before, or a type of integral that we've seen before, nothing new here. This becomes 1/4 u minus 1/4 sine of u. And then we trade in our u's for x's. Remember, u is 2x, so we get 1/4 times 2x minus 1/4 sine of 2x plus c. And I'm happy if you leave it here, but if you want to remember, like, hey, we know how to simplify sine of 2x. It's the same as 2 sine x cosine x. Maybe we can use that. Yeah, we can. So combining everything again, this 1/4 times 2 to the, or 1/4 times 2x, that's just 1/2 x minus, and then 1/4 times, we said that sine of 2x is the same as 2 sine x cosine x, and I guess the 1/4 and the 2 kind of cancel out, and we get 1/2 plus c. So we started out with no odd exponents, so we used our double angle formulas. Sine squared is the same as 1 minus cosine of 2x, and then a simple u substitution got us where we wanted to go. Similarly, I'm not going to walk through the steps here because they're exactly the same as the previous, but the integral of cosine squared of x gives me 1/2 x plus 1/2 sine x cosine x plus c. Walk through that on your own time. Consider that an optional homework problem. if you can do this, sine squared x, you can do this. It's applying the same formulas in pretty much the exact same way. In fact, this brings me to just a nice kind of formula for reduction. If we have an integral of sine to the n power or cosine to the n power, we can reduce them. So an integral of sine to the n of x is the same as negative sine to the n minus 1 of x times cosine of x over n, plus a different integral with a smaller power in the sign. So n minus 1 over n times the integral of sine n minus 2. And if we don't know how to attack this right away, we can apply the reduction formula again. Same thing here on the cosine. Cosine to the n of x, that's the same as cosine to the n minus 1 times sine over n, plus n minus 1 over n times integral cosine n minus 2 of x. So let's see this in action, because these turn out to be really powerful, right? So you give me any exponent, I can just apply this kind of reduction formula over and over again and get exactly where I want to go. So let's tackle the integral of cosine to the fourth of x. And let's use the reduction formula we know. We could also maybe try and break this as to like cosine squared x squared, and then cosine squared is the same as 1/2 times 1 plus cosine of 2x. We could use double angle formulas there. But let's use the reduction formula that we just learned. All right, so here my n equals 4, because my exponent is 4. And so we know that the integral of cosine to the fourth is the same as cosine cubed times sine over 4. So this is going to be cosine cubed of x times sine of x over 4. Plus, and remember my n is 4, so this becomes 3 over 4 times the integral of cosine squared of x. So plus 3 over 4 times the integral of cosine squared of x dx. And again, to solve this integral of cosine squared, we could try and use double angle formulas, cosine squared equals 1/2 times 1 plus cosine of 2x, or we can apply our reduction formula again, this time with, I'll change colors here, with n equals 2. So then if I come back up and I look at my reduction formula, this is going to give me cosine to the 2 minus 1, so that's just cosine of x times sine x over 2. So this guy here in blue, this is the same as cosine of x times sine of x over 2 plus, and I'll look over here again, n minus 1 gives me 1 over n is 2. And then cosine to the n minus 2, that's cosine to the 0, and anything to the 0 power is 1. So I get plus 1/2 the integral of 1 dx. Integral of 1 dx, that's about as easy as they come. So this gives me cosine of x times sine of x over 2 plus 1/2 x. Throwing everything together, my entire integral becomes cosine cubed of x times sine of x over 4 plus 3/4 times cosine of x sine of x over 2 plus 1/2 x. And I suppose if you want to, you can distribute this 3/4 in here and here, but you don't have to. This is a perfectly satisfying, perfectly good answer, except for we need a plus c. Always got to have that constant of integration. So we use our reduction formulas and we make things a lot easier. But what if we have both sines and cosines with even powers, right? We know what to do if we have a sine with just an even power or a cosine with just an even power. But what if we have a mixture of the two? So sine squared of x and cosine to the fourth of x, like we have here. We're going to do some substitution. We're going to use our double angle formulas. And in general, it's usually wiser to work with the thing that has a smaller exponent because you can reduce it down quickly, or more quickly than with the larger exponent. So let's do that here. Let's apply our reduction formula. So sine squared of x becomes 1/2 times or sorry, sine squared of x is 1 minus cosine squared x. Sorry, I was thinking of the double angle formula, not just the 1 minus cosine squared x. We get something like this. Applying our old trig identities. Integral of 1 minus cosine squared times cosine to the fourth. This is the same as the integral of cosine to the fourth of x minus cosine to the sixth of x dx. And now what we can do here is break this integral apart. We get an integral of cosine to the fourth of x dx minus the integral of cosine to the sixth of x dx. And hey, we took an integral that had even-powered sines and cosines and turned it into two integrals that only have even powers, sine and cosine. Both, in this case, both of them are cosine. And now to solve each of these, we can apply our reduction formula over and over and over again. I say over and over and over again. You're only going to have to do it 3 times. So apply the reduction formula here and here, subtract what you get. I'm not going to go through that right now, but there you go. So now we can integrate any way to multiply sines and cosines together. If one of the exponents is odd, let's recall what we do. If one of the exponents is odd, we can break it apart into an even exponent and 1, and then use u substitution. Use our trig identity, and then use u substitution. That gets us where we want to go. If we only have one sine or cosine, and it has an even exponent, we can apply double angle formulas, or what's probably easier is we can just apply our reduction formulas. So if we have sine to the even power or cosine to an even power, we can apply our reduction formulas. And if we have 2 of them, cosine and sine, both with even powers, we can apply our old handy trig identity and then get it to a place where we can apply our reduction formula. So any amount of sines and cosines multiplied together, we can take the integral of. Perfect. What if there's a different one? So integral of tangent of x. We've probably seen this before. If we want to integrate tangent of x, this is the same as sine over cosine. And we can let u be cosine of x, then du equals minus sine of x, and our integral becomes the integral of minus 1 over u dx, or sorry, du, I mean. And so this is minus natural log of u plus c, which is minus natural log of cosine x plus c. Which, I suppose if we want to, we can take this and bring it in with the power of logarithms. So this is the natural log of cosine to the minus 1 of x plus c, and then cosine to the minus 1 is secant. So this is natural log of secant of x. This minus 1 here isn't inverse, so I should technically say minus 1. Like that. So that's the derivative of tangent, or the antiderivative of tangent. It's a pretty simple u substitution formula. And we've seen that before. We did that back when we learned about u substitution back in chapter 5.7, way back in the day. But a much more complicated version is the integral of secant of x. Now this one, I don't even know how somebody would come up with a way to do this. This is just, I think, an example of real ingenuity, of real cleverness. But let's walk through a way to compute the integral of secant of x. So you and I both agree, surely, that I can multiply by 1 and I don't change anything. right? The integral of secant of x is the same as the integral of 1 times the secant of x. Ow, my shoulder popped. So we can multiply by 1 and nothing changes. And a clever way of writing 1 is the following. Secant of x plus tangent of x divided by secant of x plus tangent of x. It's a really clever way of writing 1. So my integral here can become secant times this fraction. So times secant of x plus tan x over secant plus tangent dx, which combines to be secant squared plus secant tangent, so secant of x times tangent of x over secant of x plus tangent of x dx. And wouldn't you know it, the derivative of the bottom here is the top. So the derivative of secant is secant squared, the derivative of tangent is secant times tangent. So if we let u be the denominator, so secant of x plus tangent of x, then du is secant squared x plus secant x tangent x dx. We have a secant squared x plus secant tangent dx right there. So my integral becomes 1 over u du, which is natural log of u. And so we find that the antiderivative of secant of x is the natural log of secant of x plus tangent of x plus c. That's quite something. So I don't know how people thought to do this, but they did, and it worked out to be pretty spectacular, pretty great. So the reason I bring this up is we're about to see 3 antiderivatives that involve secant and tangent, and something that we're going to use is another trig identity. But I figured if we're going to be talking about secant and tangent and the trig identity that goes with, we should also talk about the antiderivative of secant because it's so clever. So let's take a look at something like this. The antiderivative of tangent cubed times secant to the 5th. And we're going to use the similar in flavor of sine squared plus cosine squared equals 1, but this time it is tangent squared equals secant squared minus 1. Okay, so how is that going to help us? Well, the way we can use this handy trig identity to help us solve this is rewrite this as tangent squared of x times tangent of x times secant to the 5th of x dx. Hey, tangent squared, that's secant squared minus 1. So secant squared of x minus 1 times tangent of x times secant to the 5th of x dx. Okay, and now I have a bunch of secants all together. I can multiply this secant in here. So this gives me the integral of secant to the 7th of x minus secant to the 5th of x times tangent of x dx. Or actually, sorry, I think I got a little bit ahead of myself. Let's maybe take this one step at a time. This is the same as the integral of secant squared of x minus 1 times tangent of x times secant to the 4th of x times secant of x, which we can move things around. I'm going to swap these two guys here. We get the integral of secant squared of x minus 1 times secant to the 4th of x times tangent x times secant x dx. And the reason I'm doing that, as we recall, is that secant times tangent is the derivative of secant. And I'm going to have here a bunch of secants all hanging out. So if I distribute this secant to the 4th in here, I get an integral of secant to the 6th of x minus secant to the 4th of x, that's in parentheses, times tangent of x times secant of x dx. So I have a bunch of secants all hanging out, and I also happen to have the derivative of secant of x, right? Because the derivative of secant is secant times tangent. So let's let u equal secant of x, then du equals secant of x times tangent of x dx. Like I said, I've already got one there. So this becomes the integral of u to the 6th minus u to the 4th du. And that's a straight up polynomial. So just about the easiest antiderivative you can take. We get 1/7 u to the 7th minus 1/5 u to the 5th plus c. And then we just need to trade our u's in for x's, and we recall that u is secant of x. So this is the same as 1/7 times secant to the 7th of x minus 1/5 times secant to the 5th of x plus c. So it's very similar in flavor to when we have sines and cosines, and the reason it's similar in flavor is because we're using a similar trig identity. So tangent squared equals secant squared minus 1. So let's see another example using that same trig identity. Secant squared equals, or tangent squared equals secant squared minus 1. Or another way to rewrite that is that tangent squared of x plus 1 equals secant squared of x. Do I have that right? Yeah, add 1 to both sides. Perfect. So this is the trig identity we're going to use for this particular problem. And how do we use it for this particular problem? Well, we're going to try and make stuff look like this, right? We're going to try and kind of force feed it to make it look like this trig identity that we want to use. So secant to the 4th, we can all agree, is secant squared times secant squared. So this becomes the integral of tangent squared x times secant squared x times secant squared x dx. And I can make one of these secant squareds turn into a tangent squared plus 1. So I'll go ahead and make the middle guy turn into tangent squared of x plus 1 times secant squared x. And how does this help us? Well, kind of how in the previous example we used u substitution, and in the previous example we wanted to be left with a tangent times secant here because the derivative of secant is secant times tangent. Well, remember that the derivative of tangent is secant squared. So we want to be left over with a secant squared at the end and turn everything else into tangents. And that's exactly what we've done here. Now I'm just going to distribute this tangent inside. We get tangent to the 4th of x plus tangent squared of x, all in parentheses, times secant squared of x dx. And we've massaged our integral a little bit, and it gave us a really nice u substitution. So now we can let u be our tangent of x, and then du equals secant squared x dx. Our integral becomes the integral of u to the 4th plus u squared du, and that's 1/5 u to the 5th plus 1/3 u cubed, which trade in are used for x's. We get 1/5 tangent to the 5th of x plus 1/3 tangent cubed of x plus c. Okay, so we can treat tangents and secants in a similar way that we can sines and cosines. And as such, you might be wondering, hey, is there like a reduction formula for tangents and secants in the same way there is for sines and cosines? And the answer is yes. So here's a reduction formula for tangent. The integral of tangent to the n of x is tangent to the n minus 1 of x over n minus 1 minus the integral of tangent to the n minus 2. So this is a lot simpler than the first one, than the previous reduction formulas we saw. Let's see it in action. So we want to find the integral from 0 to pi over 4 of tangent cubed of x dx. Well, this is the same. Well, we know that the integral of tangent cubed, applying this reduction formula, my n is 3 because my n is the exponent. So this becomes tangent squared of x over 2. So we get tangent squared of x over 2 minus the integral of tangent to the first power of x. So minus tangent of x dx, this integral. And so we get tangent squared of x over 2 minus the natural log of secant of x. No need to add the plus c here. This whole thing is evaluated from 0 to pi over 4. And now we just plug in our stuff. So we're going to get tangent squared of pi over 4 over 2 minus the natural log of the secant of pi over 4 minus tangent squared of 0 over 2 minus the natural log of secant of 0. And let's go ahead and work over here first. Pi over 4, that's the place, that's 45 degrees, that's where sine equals cosine, so the tangent of pi over 4 is 1. If we square 1, we get 1, so we get 1/2 minus, and then I don't know how well you remember your unit circle, but the secant of pi over 4 is square root of 2, so we get minus natural log square root 2 minus tangent of 0 is 0, so that's kind of handy, minus secant of 0 is 1, right? Because secant is 1 over cosine. Cosine of 0 is 1. 1 over 1 is 1. But the natural log of 1, ln of 1 is 0. So here I get 0 minus 0. So that all cancels out. And our final answer is just 1/2 minus natural log square root of 2. So those are different integrals with a lot of different trig functions all involved, and how we can simplify them to get other integrals of trig functions involved, and then simplify those with u substitutions or double angle formulas. Thank you so much for watching.